Thermal Testing and Verification, Part 3. In this part we will address spacecraft level testing and verification. We will cover spacecraft level test objectives, test temperatures, the thermal balance test, and correlation of the spacecraft thermal math model to test data. This lesson will describe the thermal tests that are typically performed at the spacecraft level. The facilities and methods by which these tests are accomplished will be discussed in Part 4. In this part, thermal vacuum, thermal balance, and thermal cycle testing of spacecraft will be described, along with government requirements for those tests. The process by which appropriate test temperatures are established based on allowable temperature ranges of spacecraft components will be discussed. Finally, the process by which thermal math models are correlated to thermal balance test data will be outlined. Spacecraft level tests, also known as system level tests, have a different emphasis than unit or subsystem tests. At the spacecraft level, emphasis is on final ground verification of the system and unit performance in a flight-like environment. The focus is not on individual unit functionality, but rather on end-to-end performance verification of subsystems. Interfaces between units and subsystems, the continuity of mission objectives, compatibility of different subsystem requirements, and overall flight worthiness of vehicles are demonstrated. At the qualification level, thermal vacuum, thermal balance, and thermal cycling are performed, typically in one integrated test. In thermal vacuum phase, functional performance tests demonstrate the ability of vehicles to meet design requirements under vacuum and at prescribed temperature extremes, plus a specified margin. In the thermal balance phase, data are gathered for thermal math model correlation and verification of the thermal design and hardware. In the thermal cycling phase, temperature cycling provides environmental stress screening for detection of hardware design defects. At the acceptance level, thermal vacuum and thermal cycle testing are performed. Thermal balance testing is a good idea, but is not always required because the thermal design and thermal math models will have been previously demonstrated at the qualification level. During acceptance thermal vacuum phase, functional performance tests are conducted to prove workmanship quality and flight worthiness. This is different than the qualification thermal vacuum test where the design robustness is being proven. During the thermal cycling phase, temperature cycling provides stress screening to expose workmanship and manufacturing process defects. At the spacecraft acceptance level, the primary focus is on thermal vacuum tests, which emphasize proving the flight worthiness and system performance of the vehicle in a flight-like environment at the system level. The vacuum environment provides the most realistic flight conditions in which to verify functional performance. Thermal gradients, temperature extremes, and hot and cold spots are most accurately captured at the spacecraft level in a simulated space environment. A secondary focus of spacecraft level thermal testing is thermal cycling, which emphasizes stress screening to detect manufacturing workmanship problems. Ideally, most of this screening would have been accomplished through a thorough test program at a lower level of assembly, such as at the unit level. This is because problems are extremely costly to fix once a program reaches system-level tests, which is typically on the critical schedule path. Testing at the spacecraft level is also less effective because the rapid rates of temperature change needed to force a defect to become visible can be difficult or impossible to achieve with a full spacecraft. While government test standards discuss spacecraft-level qualification testing using a non-flight spacecraft, it is rarely performed in practice due to the high cost of building a spacecraft that will never be flown. The most common practice for one-of-a-kind spacecraft, or the first spacecraft produced in a series of identical spacecraft, is the proto-qualification test. Acceptance testing is typically for the second and subsequent spacecraft in a block buy. With our protoqual or acceptance, the spacecraft level test demonstrates system performance in a vacuum, at or near the maximum and minimum expected flight temperatures, plus applicable margin. The test detects material, process, and workmanship defects. If a rigorous unit-level test program has been established, emphasis at the system level is on mounting, cabling, connectors, and unit and subsystem interactions. However, defects that have been managed to slip through unit-level testing may also be uncovered during system-level tests. Functional verification of the thermal control subsystem hardware is another important objective of spacecraft-level testing. To accomplish this, abbreviated tests are typically performed during one temperature cycle to exercise heater control circuits, demonstrate heater control authority, and verify heat pipe performance. Thermal control of propulsion subsystem components, especially propellant lines, can be challenging, making it especially important to verify propulsion subsystem functional performance during a spacecraft-level test. These thermal subsystem test objectives are accomplished as part of the system functional testing at temperature plateaus and during temperature transitions. For spacecraft undergoing acceptance testing, the spacecraft thermal design has previously been verified by thermal balance testing of the qualification or proto-qualification vehicle, but build-to-build variations can have thermal impacts because the installation quality of thermal control hardware is highly sensitive to individual technicians' performance. Therefore, workmanship verification is still important and must be accomplished during spacecraft acceptance testing. Workmanship-sensitive manufacturing processes that are difficult to control include installation of thermal interface materials, which affects contact conductance, wrapping of tapes and heater elements, MLI compression, seams, overlaps, gaps between optical solar reflector tiles on radiators, attachments of thermostats, sensors, and patch heaters, the thickness and area of optical coating such as paints, and the effects of installation on surface optical properties. As was the case at the unit and subsystem levels, spacecraft level tests have specific requirements that are typically levied by the customer. The goal is usually to reach the same acceptance, protoflight, and qualification temperature ranges that were applied at the unit level, but the actual spacecraft temperature cycle range is usually limited by units within the spacecraft that reach their allowable limits first. Government customers have specific requirements for minimum number of temperature cycles, dwell periods, and thermal balance phases. A typical spacecraft thermal vacuum test is required to have 4 temperature cycles with 4 to 24-hour dwells at plateaus, although the actual dwells can reach weeks in duration in order to test particularly complex spacecraft. Government customers typically require a minimum of 2 or 3 thermal balance phases, but it is not uncommon for programs to do many more. JPL conducts all spacecraft-level tests at acceptance temperature levels. As noted earlier, qualification testing at the spacecraft level is rarely performed these days due to the high cost of building a non-flight spacecraft. Here we see an example of the spacecraft thermal vacuum test profile for one particular program. In this case, the test begins with 9 thermal balance phases and is followed by 4 thermal cycles in which full functional testing is performed on the last cycle. Other programs may follow a different test sequence and will typically not have this many thermal balance phases, but the profile shown here serves as an example of the concept. We will now take a moment to discuss how target temperatures are established for spacecraft-level tests. This is not as straightforward a process for spacecraft as it is for individual unit tests. When testing at the spacecraft level, the objective is to get as many units as possible to their individual protocol or acceptance temperatures, with more benign test temperature plateaus sometimes established to demonstrate in-spec performance. To accomplish this, the spacecraft is divided into thermal control zones, such as individual equipment panels or heater control zones. Each of these zones will contain a number of different units. We do not want to exceed test temperature limits for any units, so the unit that reaches its temperature limit first is used to control the heating or cooling of that zone. The first thermocouple in a zone to reach the test temperature establishes when the entire zone is at the test temperature. Unfortunately, this results in most units within a zone being tested at a less stressing temperature than in unit level test, which illustrates the importance of complete unit level testing. Here's a hypothetical example to illustrate the concept of zone thermal control. Say we have 3 units mounted together on the same equipment panel that establishes a thermal control zone. Each unit has a different acceptance temperature range, and pretest thermal analysis predicts a different temperature range for each during the test. If we take the warmest minimum temperature and the coldest maximum temperature for each, and add analysis uncertainty margin and tolerances for test measurement and control, we find that we might end up with a test temperature cycle range that is only around half the range that the individual units experience during their unit level testing. A real-world example comparing unit acceptance temperatures to what those units were actually able to reach in spacecraft level testing is shown here. This illustrates the importance of a good unit level test program. Functional testing is performed throughout a spacecraft thermal vacuum test and can account for most of the testing time. Functional tests are typically performed prior to chamber door closure to ensure readiness to proceed with the test. Complete functional testing is desirable during the first and last cycle at both hot and cold temperature limits and is required for DoD programs. Abbreviated functional tests are required at hot and cold temperature limits for intermediate cycles. A final functional test is performed after the chamber comes to ambient and the chamber door is open. All spacecraft electronics should be on and operating during all portions of the test and should be programmed through various operating modes with perceptive parameters being monitored and recorded. The only exceptions to this are the pump down period when high voltage units should be turned off to avoid electrical arcing, and during transitions from hot to cold when some units may be powered off to accelerate the cool down and reduce test time. DoD allows units to be turned off during cool down, but only after the temperature has dropped below the minimum expected flight temperature. While turned on, operating times should be divided approximately equally between primary and redundant circuits or units. Next, we turn our attention to spacecraft level thermal balance test. Spacecraft thermal balance testing is usually performed as part of the system qualification or proto-qualification thermal vacuum test. The primary objectives are to obtain test data for correlation to the thermal math model and to verify the thermal design. Both steady state and transient temperatures, heater power usage, and electronic box power dissipations are recorded to aid in math model correlation. The thermal balance test also verifies the thermal control subsystem design by showing that components remain within their allowable temperature limits, that interface temperature requirements are met, and that thermal gradients are as expected. Performance of the thermal control subsystem hardware is also demonstrated during thermal balance tests. For heaters, current draw is measured and control authority margin is demonstrated. The location and functionality of thermostats is verified. Radiator and heat pipe sizing and operation is confirmed. Louvers, phase change materials, interface materials, and cryocoolers are shown to be functioning as expected. Flight temperature sensor accuracy is assessed, and thermal control software and commanding are exercised. Here we see an example of the sort of data that is gathered to assess heater operation. Temperature sensors on a solar array hinge damper assembly show temperature cycling as expected under the influence of thermostatically controlled heaters. If this data is plotted on a small time scale, the heater on time can be divided by the time to make one on-off cycle to determine the heater duty cycle. This can then be compared to the maximum allowable duty cycle to assess compliance with program margin requirements. A minimum of 3 test phases are usually required: a hot and cold case to correlate the thermal model to, and a third case to show that the correlated model can accurately predict temperatures for conditions other than the two to which it was correlated. The most common cases chosen for thermal balance testing simulate the worst hot case and worst cold case operating conditions, with a cold non-operating case that allows survival heater verification. Additional cases are added as necessary to assist thermal math model correlation, capture transient data, simulate eclipse conditions, aid software verification, etc. Test phases are usually specified for bounding worst-case conditions. These need not be established as absolute worst-case conditions, but should be similar to the driving thermal design analysis cases, which include realistic worst-case combinations of factors such as season, equipment duty cycle, solar angle, and eclipse conditions. Spacecraft component internal dissipation, voltage, and environment are typically held constant to provide steady-state conditions. Components cycling on thermostats will achieve a pseudo-steady state where temperatures cycle up and down over the same range and with the same period in a repeatable fashion. Here we see an example of a thermal balance test profile that includes 12 cases, enveloping the entire range of thermal conditions expected over the mission. This is an unusually large number of cases, but is well justified for a spacecraft that can experience many markedly different operating modes or environments. For each thermal balance phase, temperatures for all test thermocouples and flight thermistors are recorded once all have reached equilibrium. Ultimately, it is a thermal engineer that decides when equilibrium has been achieved, although a guideline, such as less than ½ degree C per hour, should be established prior to the test. No cycling of equipment power or environmental heaters is usually permitted during equilibrium phases so as to achieve a true steady state. For conservatism, thermal balance may be approached from a more extreme condition. For example, one can cool a spacecraft to below the expected thermal balance temperature and then allow it to warm to thermal balance. If steady state is declared too early, the measured temperatures will be a little on the low side, which would be conservative for a cold case test. Heater duty cycle data is also taken for math model correlation and heater subsystem verification. During transient phases, temperatures are taken starting from a known equilibrium state and then through the entire transition. The endpoint of a transient phase need not be an equilibrium phase, but spacecraft component power should be held constant until the transient phase is completed for all components. During thermal balance testing, it is important to exercise all important heat flow paths. This includes heat flow across heat pipe interfaces and critical unit to mounting surface interfaces, especially for high-power units like traveling wave tubes, or TWTs. The spreading of heat onto radiator surfaces should be confirmed to be as expected, and temperature gradients on equipment panels should be measured. Success requires that time be spent before the test identifying all critical heat flow paths, and that the test phases are implemented to verify them. It is important to obtain operational response data for temperature-sensitive and mission-critical equipment. This may require a dedicated test phase to impose specific environmental conditions. Our final topic for Part 3 is thermal math model correlation. Thermal math models are correlated through a combination of analysis and gathering of test data. Prior to the test, spacecraft temperatures and heater power usage are predicted for the planned test configuration and environment. During each phase of the thermal balance test, spacecraft temperatures and spacecraft heater duty cycle data are recorded for comparison to thermal math model predictions. Test configuration information must also be recorded. This includes data such as spacecraft bus voltage, electronic box operating modes, chamber cold plate temperatures, test heater power, etc. They are needed to confirm the test conditions were as assumed in pretest predictions. Thermal model predictions are then updated to reflect the as-run test configuration prior to start of model correlation. The thermal math model is correlated by adjusting model parameters within a reasonable range to bring predictions into agreement with test data. Conduction and radiation heat transfer paths are often adjusted, but the spacecraft geometric math model is rarely modified. All changes that are made to the model must be justifiable and reasonable. Each thermal balance test phase is correlated to the model predictions separately. With each new correlation phase, care must be taken such that new adjustments do not destroy the correlation achieved in previous cases. What constitutes acceptable correlation varies from organization to organization, but plus or minus 3 to plus or minus 5 degrees C is typical. Correlation criteria for heater power are generally not specified, but criteria on the order of plus or minus 10% have been used in the past. Following correlation, final flight temperatures and heater duty cycle predictions are made. Compliance with thermal uncertainty or allowable flight temperature margin requirements and heater control authority are demonstrated by analysis with the correlated model. Any non-compliances require that hardware or operational changes be made to maintain margin, or a waiver granted after an appropriate review of the risks involved. Despite being correlated to test data, the thermal math model still has inherent uncertainties that must be mitigated by margin. Residual flight temperature uncertainties are the result of correlation tolerances and test unknowns. Unknowns include spurious heat sources in the test chamber, the limited number of test cases, absorbed heating estimates coming from indirect techniques, instrumentation inaccuracy, individual component dissipation inaccuracy, inability to capture end-of-life thermophysical properties, test cable and support structure losses, and test equipment interference. Also contributing to residual uncertainty is the unfortunate fact that the thermal design changes that sometimes result from testing are rarely verified by retest due to cost and schedule pressures. Other routine vehicle hardware changes such as box changeouts and addition of flight equipment that could not be tested in the chamber also add uncertainty. In our discussion of spacecraft-level thermal testing, we will have learned that while defects in individual units may be discovered in spacecraft-level tests, the emphasis is on interfaces and end-to-end verification of the system. During the test, the goal of bringing as many units as possible to their target temperature is accomplished by setting up a number of thermal control zones within the spacecraft that can be independently driven to different temperature levels. We also learned that vacuum thermal cycling is required on most programs, most commonly for 4 thermal cycles, and that thermal balance testing is required to correlate the thermal math model and verify the thermal design. This concludes Part 3 of this lesson. In Part 4, we will discuss space environment simulation techniques.